For directional derivatives in the gradient, let's use this specific example, which I know we talked about before. It's the function z or f of xy equal to 9 minus x squared minus y squared, which I think of as a mountain, right? It's a paraboloid opening downwards, but you can also think of it as a mountain with the peak of the mountain at the point 0, 0, 9. And I'm going to try and draw a decent job of drawing this. So here's my 0, 0, 9 point. It's going to come down like this, down like this. And then let's just kind of draw it. Draw that like that. Let's see. There's a specific point I want to draw, which is like, that's not, let's go like right up there. Sure. And then here's my x-axis coming out at us. I'm going to erase this part with the extending down because I don't really need all that for this. Although, of course, right, the paraboloid does go on forever and ever and ever. So it extends downwards. And we've got some points. Specifically, this is the point 0, 0, 9. This is the point 0, 3, 0. Here you've got 0, negative 3. So right, you could go on and on. Here's 3, 0, 0. And I don't really want all this. You can have that. We don't really need it. And then we've got this point on the graph, which is over. So 1 in the x direction, 2 in the y direction, and 4 in the z direction. So that point right there, that's the point 1, 2, 4. And we're going to talk about a number of things at that point. Specifically, well, let's remind ourselves what we talked about last time. So we talked about the partial with respect to x, which gives you the slope in the x direction. So that's fx. That's going to be, well, the partial with respect to x is negative 2x. And if we find the partial evaluated at that point, so fx evaluated at 1, 2, 4. I thought I was looking at something weird there. Oh, that's fine. I'm just going to get negative 2 times 1, which is negative 2. So again, right, if we're at this point, which is like on the front side of the mountain, and we move in the positive x direction, our slope is going to be negative because we're going to be going downwards. On the other hand, just as kind of a counterpoint, pun intended, if instead I went back 1 over 2 and up 4, so instead if I was like maybe back there behind, right, like, so the side of the mountain that we couldn't see if it was like we were looking at it like this, if someone's over there, if they move in the positive x direction, so if they're at the point negative 1, 2, 4, if they move in the x direction towards you, their slope of their tangent line is going to be positive 2 because they have to come up over the mountain before they get to the other side. And that's because, right, fx evaluated at negative 1, 2, 4 is going to be negative 2 times negative 1, which is positive 2. So, right, so your partial derivative evaluated at a particular point clearly depends on the point, right? But you're always moving, at least for fx, in the forward direction, the at you, coming right at you direction. Okay. And then, of course, we also saw that at this point, fy is negative 2y, and fy evaluated at 1, 2, 4 is equal to negative 2 times 2, which is negative 4. And again, that's because at this point, right, if you move in the y direction, you're still moving down the hill, but actually at a steeper slope because you are kind of, I know it's hard to tell with this picture, but you're kind of what's the word I'm looking for? You've moved you're further away from the center in the y direction, so you're kind of further down in the y direction, meaning it's already like you're not like right up here, like the slope is not very steep, and as you move further down, the slope gets steeper. So if you're further down in the y direction than you are in the x direction, right, you're going to have a steeper derivative in that direction. So the things we're kind of interested in here are, well, actually, I should point out this circle here is the level curve for z equal to 4, right? We set z equal to 4, and you just get a circle. And we want to know, like, what's the derivative in a different direction, right? Maybe I don't want to know what the derivative in the x direction or the y direction is. Maybe I want to know what the direction is, the derivative is in, maybe say like the 2 forward and 3 over direction. It's still going to be negative because we're clearly going to be going down the hill, but that's what I want to know. So I want to know what's the derivative, aka what's the slope of the tangent line in the direction of the vector 2i plus 3j. And I'm going to try and draw this, although it's not going to be super great. Let me just try and draw the tangent line here. So let's say we're coming like kind of, right, there's our tangent line that is moving in that direction. It's moving 2 forward and 3 over. It's not super easy to draw these things. So that's the idea. So first of all, we need it to be a unit vector for reasons you'll see. So let's say that the unit vector, well, I'm just going to take this vector and divide by its magnitude. Its magnitude is the square root of 4 plus 9, right? It's 2 squared plus 2 squared. So the unit vector is going to be 2 over root 13 I plus 3 over root 13 j. I feel compelled to actually show you where the calculation comes from. I could totally just tell you, and some of you already know how they calculate the directional derivative, but I feel like it's worth actually seeing the process of it. Just if you see where it comes from, you're more likely to remember it. Whereas if you just memorize the formula, it's easier to forget it. So I'm going to show you where it comes from. Let's see. I'm going to erase all this. I'm going to give you a top view. So I'm going to give you a top view of the level curve. Here's my x, here's my y. Not how I really want it, yeah. And here's my level curve is z equal to 4. That's a circle of radius square root of 5, right? Because if z is 4, you get x squared plus y squared equal to 5. This is x squared plus y squared equal to 5. And I'm interested in what's happening at the point 1, 2, 4. Well, we're already on z equals 4, so I'm really just interested in going over 1 and up 2. Looks kind of high, oh well. So from that point, I want to go in the direction of 2i plus 3j. I feel like the picture there is not particularly excellent, but that's fine. So I'm going over 2 and up 3. It's not really to scale, that's fine. Because really I actually want the unit vector in that direction. I just need the slope to be right. So maybe it's more like about this. There's my unit vector. And again, it's just that vector there. Nothing I need to write it again. So I'm trying to figure out, right, from that point there, if I move out into space, gosh, so right. If I'm moving outwards, but still in the same plane, what direction are we going? What's the slope of our tangent line? Well, the way I'm going to find that is by doing the following. I am going to parameterize the line through the point 1, 2 in the direction of u. Say that again. So, right, this is the point 1, 2. And from that point, we're going in the direction of this vector 2 over root 3i plus 3 over root 13j. So I'm going to find the equation of the line through that point, which I'll point out does not go through the origin. Okay, so that line, well, it's easy to parameterize a line, right? In fact, that's how we write lines in three-dimensional space. If we know a point and the direction, the line is just, let's see, the point, so the point 1, 2, and then plus the x portion of the vector times t, so 2 over root 13 times t, plus, and then this part is going to be plus 3 over root 13 times t. That'll get me any point on this line. Okay, so now here's what we're going to do. To find the rate of the rate of change of this function in that direction, we're going to take the directional derivative. Excuse me, which is going to be the following. Well, I'm really just trying to find the derivative of this line. Well, that's going to be df dt. Does that seem reasonable? Right? We're saying our function is this function, and we're asking, right? So again, I should say, right, going that way, right? So here's our line. Right there is where time equals 0. And then as time increases, we're going that way. And as time we're decreasing, we're going that way. So as time increases, we're moving that way, which is like moving out along this black arrow. But we still have to stay on the surface. So when we find df dt, we're really finding literally what the slope of the tangent line is in the direction of what? Of the direction we move when t increases, which is along that line. Okay, so we know how to find this derivative. We're going to use the chain rule. Sorry, I'm kind of trying to stay on this side just because I don't want to. I feel like it's nice to have this picture here. So to find the chain rule, well, we have that f is a function of x and y, and both x and y are functions of t. So we can say that, let me move this over here so I have room to write it. Sorry, I know I erased the vector u. Let me write it again up here just so we have it. Well, I guess it's right there. Right, u is 2 over root 13I plus 3 over root 13j. So the directional derivative in the direction of that vector u is df dt, which is just the chain rule, right? F depends on x and y and x both depend on t. So it's going to be del f del x times dx dt plus del f del y times dy dt, which we can totally calculate. Before we calculate it, I want to point out that there's another way to write this. This is literally the dot product of the vectors del f del x comma del f del y dotted with dx dt dy dt. And now take a look at this. So the vector consisting of the partial derivatives is called the gradient. So this is your gradient of your function f, which we write using the upside down triangle symbol. So that's the gradient of f. It is a vector, right? So I want to be very, very specific here. The gradient of a function is a vector dotted with the vector consisting of the derivatives of everything with respect to t. But hey, wait a minute. If you look at the line that you've got here, the derivative of x with respect to t is just that. The derivative of y with respect to t is just that. So when you put these two together, you get the vector 2 over root 13, 3 over root 13. But that's exactly the vector that's the direction vector that we're taking the derivative in. So, long story short, the directional derivative of the function f in the direction u is the gradient of f evaluated at the point we're interested in, dotted with the vector u. So for this particular problem, again, where f of x is equal to 9 minus x squared minus y squared, and the vector u is 2 over root 13 I plus 3 over root 13 j. The gradient of f in general is the vector, and you can write this like in any way you want. You can write it as the vector negative 2x, negative 2y, or you could write it as the vector negative 2xi plus negative 2y j, right? There's like a million different ways you can write a vector. In either case, del f dotted with u. So when you dot vectors together, you just multiply the I components and the j components, the k components if you have them, and then add them together. So this is going to be negative 2x times 2 over root 13 plus negative 2y times 3 over root 13. Now, I should point out, this is the gradient of, this is the directional derivative of f in the direction of u at any point on the function. But we specifically wanted the directional derivative in the direction of u at that point there. So we're going to plug in negative 1 for x, 2 for y, and 4 for z if it makes sense to you. It doesn't make sense to plug. There's no plugging in 4 for z. So, yeah, let me write it this way. And the notation here starts to get kind of weird. So this directional derivative evaluated at the point 1, 2, 4 is equal to negative 2 times 1 times 2 over root 13 plus negative 2 times 2 times 3 over root 13. So that's going to be what? Negative 4, that's going to be negative 12, so we're going to get negative 16 over the square root of 13. So that is going to be the slope of this line that is tangent to this surface in the direction of this vector, 2i plus 3j. Okay, let me pause for a moment and ask you, are there questions about this so far? It's okay if there aren't, but I know this stuff can be confusing. Okay, let's ask a few more questions still related to this picture. So I want to change it up just a tiny bit. Yeah. Sorry, I'm like, do I want to erase anything? Yes, I can. I don't really want to erase any of this. Sure. Yeah. So let's ask the following questions. Fine. We don't know this. So now I want to ask the question instead, what is the slope at the point 1, 2, or 1, 2, 4? So same point. We're still at the same point here, but now instead of going in the direction of 2i plus 3j, now I want to ask what's the slope in the direction of, I don't know. Now, I will tell you, I usually, when I took this class many years ago, I always remember the direction vector be given like just as a vector, meaning not normalized. So I would usually be saying like, what's the direction of, or what's the slope at this point in the direction of u equal to, say, the vector negative 3, negative 4. That's not a unit vector. So here's what we have to do. Say, well, I know that it's going to be, again, right, it's going to be del F, which I feel like usually got an arrow over it, but maybe not. Del F dotted with U, but normalized. So U divided by its own magnitude. And I wish to say del F evaluated at 1, 2. Okay. We know what del F is. Del F is just negative 2x, negative 2y, evaluated at 1, 2. So that's going to be negative 2x is negative 2. And then negative 2y evaluated at 2 is going to be negative 4. So minus 4j. So there's your del F dotted with your unit vector in the direction of u. So take this vector, negative 3i minus 4j, and divide it by its magnitude, which is 5, because it's the square root of negative 3 squared plus negative 4 squared. So that's going to be negative 3/5 I minus 4/5 j. And then we dot it together. So dotting it together, I get negative 2 times negative 3/5, so it's going to be positive 6/5. And then plus negative 4 times negative 4/5, which is plus 16/5. Which is going to be 22/5. So on mount derivative here, at this point, if instead of moving in the towards you direction and the to the right direction, right, in the 2, 3 direction, like we did the first time, now we're moving in the negative 3, negative 4 direction. So we're kind of moving, right, not exactly towards the top, but certainly in a way that's going to be going up the hill, right? We're going in and over. I mean, it actually might be exactly towards the center. No, I don't think so. No, it's not. Right, so that makes sense that if we're going up the hill, the directional derivative should be positive because, right, we are ascending the hill and our slope of our tangent is positive. I will also mention, just because it seems reasonable, if you change if you make the directional derivative in the opposite direction, right? If I said, what's the directional derivative if our vector u is not negative 3i minus 4j, but positive 3i plus 4j, it's the same calculation, but the only thing that's going to change is these are both going to have the opposite signs, which means this is going to be a negative and a negative. So if you change just to the opposite direction, your directional derivative is exactly going to be the opposite value of what it was, which makes sense because you're literally just saying, instead of going this way, I'm going to turn around and go that way. So the slope, right, if you're facing upwards, the slope going up is the opposite of if you turn around and face downwards, the slope's going down. So if you're at the same point and you just change directions, the slope just becomes the opposite of what it was. Same thing is true. No, you can't really say the same thing is true. I mean, I guess you could kind of. No, that's a bad analogy. I'm not gonna say those wrong things. Okay, a couple other questions to ask. We might actually be done with this question at some point. So you could also ask. This is going to seem kind of silly, maybe, but it's worth recognizing. What's the slope? Again, at this point, 1, 2, 4, in the direction of the vector. What have I got here? The 1, 0 vector, the unit vector in the x direction. Well, not surprisingly, right, if you do del f dotted with u, right, that's going to be, well, again, del f was, right, there's your del f, negative 2i minus 4j. It hasn't changed, right? We're still at the same point. The gradient's still the same. Right, you take the partials, it's negative 2x, comma negative 2y at the points 1, 2. So the del f, that's going to be negative 2i minus 4j dotted with the vector u, which is going to be 1i plus 0j. If you dot those together, you get negative 2 times 1 plus negative 4 times 0, which shouldn't be surprising at all, because the directional derivative in the direction of I, also known as the direction of x, that should just be equal to the partial derivative in the direction of x evaluated at the same point. So if you do the directional derivative in one of your usual x or y directions, you're just going to get the partial derivative with respect to that variable evaluated at the point. Okay. So a couple last, well, not last things, but a couple kind of last general things here. So if you're at this point, 1, 2, 4. So at the point 1, 2, 4. What direction do we have to travel to get to the summit the fastest? All right, well, I'm trying to go straight to the middle, right? So again, here's my level curve. I'm at the point 1, 2, I know z is equal to 4. And I'm trying to go that way. Well, if I'm trying to get to the summit the fastest, it means I'm going in the steepest direction, right? I'm not going like around and around the mountain using switchbacks or whatever. I'm going straight up the mountain the steepest way possible, because the steepest way is the fastest way to the top. Because you're right, if you're going the steepest way, your slope is the greatest, meaning you're getting the most elevation for the least amount of over. All right, well, how am I going to calculate this? I can see from the picture that the direction is definitely just inward. So if I'm at the point 1, 2, well, I kind of want to go towards the origin. So from 1, 2 to the origin, I can literally just calculate that vector. That vector is going to be, well, 0 minus 1, 0 minus 2. I do need to normalize or unitize it, so I want to make it, let's see. The magnitude of this is the square root of 5, so negative 1 over root 5, negative 2 over root 5. And I should not be saying these are equal. They're not equal to each other. I want this. So there's my direction vector. And what do I want to say here? Sorry. Oh, yeah. So notice, sorry, I'm trying to think. There's something here that I've written that I'm like, what am I saying here? Okay, yeah, that's the thing I want to point out. So, yeah. So the direction that's the steepest is towards the peak. But here's the thing that's kind of interesting to notice. If you actually look at the gradient at this point, 1, 2, 4, well, again, the gradient is negative 2x, negative 2y as a vector. It is a vector. Evaluated at the point 1, 2, 4. We're going to get negative 2, negative 4. But look, these vectors are multiples of each other. They have the same direction, right? If we unitize or normalize this, right? Here we see that if you take the direction u and you normalize it, you get exactly negative 1 over root 5, negative 2 over root 5. If you take the gradient and normalize it, you get the same thing. You get negative 2 over the square root of 4 plus 16, which is 20, comma negative 4 over the same thing. But that and that are literally the same, right? Square root of 20 is 2 root 5, and 2 over 2 root 5 becomes 1 over root 5. Same deal here. So here's the takeaway. The gradient always points in the direction of steepest ascent. I'm going to say that again. Write it down. So the vector, which I'm going to write with an arrow on top just to make it super clear, it's a vector. The vector, which you can write as you know, del f, del x, comma, del f, del y, evaluated at your x, comma, y, always points in the direction of steepest ascent. Which is kind of neat. I also think, and I'm just kind of, right, there always should, unless you're at the top, right? If you're at the top, I guess, right, the direction of steepest descent is the same for anything, right? The top, the gradient would be 0. Yeah, actually putting in 0, 0. But the direction always, so the gradient always points in the direction that is the most positive slope. And if you want to find the direction of steepest descent, or if you want to find the direction you go in that's easiest, that's going to get you downhill fastest, that's going to be the negative of the gradient. So the negative of the gradient always points in the direction of steepest descent. Okay, that's kind of neat. The other thing that is really worthwhile to know is that the steepest slope you can have is the magnitude of the gradient. So the maximum of the directional derivative, right, at a point. So if you're saying I'm at a point on the mountain, right? I'm at this point on the mountain, and if I go in the direction that's steepest, what slope am I going to be traveling up? Well, that slope, if you go in the direction that is steepest, the direction of the gradient, will always be the magnitude of the gradient. Why does that work that way? Well, let's check it out and see. So we know, first of all, that if you're going to maximize the directional derivative, you want to be going in the direction that's steepest, which is the direction of the gradient. So I'm going to be doing the gradient dotted with the unit vector in the steepest direction. But hey, we know what that is. We know that the direction, oh, actually, I was going to do something else. Sure, I guess that's fine. I was just going to write, no, that's silly, I guess. You could, so there's a couple, I was thinking of it a different way. There's a couple ways you could do this. Sure, okay, fine. Let me show you 2 ways, because now I'm like, my brain's like both ways. So it's been a while, I know, but the dot product, one way to calculate the dot product is to say it's going to be the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them. But well, I guess if we want to maximize this, right? First of all, that's a unit vector, its magnitude is 1. Second of all, this is going to be maximal when cosine is as big as possible, which is when the angle is 0, because cosine is 1. So this is maximum occurs when the angle between the 2 vectors is 0 degrees or 0 radians, which is going to give you a maximal value of that times 1 times 1. So the maximum value of the directional derivative is the magnitude of the gradient. And it occurs in the direction of the gradient. Kind of neat. The thing I was going to say that my brain was going to is I was going to say, okay, well, I already know the direction, so I'm just going to say that the vector u is the unit vector in the direction of the gradient, which would be del f divided by the magnitude of del f. And then when you dot that with del f, you get del f dotted with del f divided by the magnitude of del f. But a vector dotted with itself is its magnitude squared. And so if you take the magnitude squared divided by the magnitude, oh, you get the magnitude. That's another way you can say it. Okay, so long story very short. The direction of steepest descent is the direction of the gradient at whatever point you're at. And the magnitude of steepest descent is the magnitude of the gradient. Or I should say, the steepest slope is the magnitude of the gradient. All right. Lastly, worth mentioning, just because it's in my notes here, is that if you look at the, again, the directional derivative, which is the gradient dotted with the unit vector in whatever direction, you can make this equal to 0 if the vectors are perpendicular to each other. So basically, the gradient is always perpendicular to a level curve. So right, if you look at this level curve one more time, there's my level curve, right? Z equals 4. Here's my point 1, 2. And the gradient is pointing in that direction, right? And something perpendicular to that, well, again, if you're perpendicular to a radius of a circle, you're tangent to the circle. So, and if we're traveling in the direction that's tangent to the circle, if I'm traveling in this direction here, I'm just staying on the level curve, meaning my height isn't changing, right? I'm not going up or down. So if you travel in the direction that's perpendicular to the gradient, you're essentially staying on your level curve because you're not having any change in your function value. The rate of change is 0. Okay, so the idea there is that if you're thinking about a contour map, like an actual, God, my hair is like, there's a little piece right here. Okay. So if you've got like a map that's like, say you've got like some peak, and I'm not very good at drawing these things. Wow, I'm really not good at drawing these things. But right, you can imagine like you've got some contour map. And the idea is that if you want to go up the hill the fastest, you want to cross the lines the fastest, right? So traveling, right, like if I started, here, traveling this way is not going to get me up the hill very fast because right, I'm taking a lot of distance to go up each contour line. And each contour line is supposed to represent the peak at the same height or the same level curve. But if I travel like from here, if I travel like, kind of perpendicular to the, what's the word I'm looking at? Perpendicular to the contour lines, perpendicular to the level curves, that's going to be the gradient. It's going to be the direction of steepest descent. Okay, I think I've said it enough times, maybe. Now attack, it's 224, okay. All right, let's do another example. And then I'm almost to the point where I can get to answering question 27 from section 14.5. I think I'd have to look at it again. Let's look at a couple more examples. So let's say we've got this function f of x comma y is equal to xy plus y squared. And I'm looking at the point 3, 2. You can write just the xy coordinate 3, 2, or you could say it's 3, 2, comma, let's see, 6 plus 4 is 10, right? Either way. So I want to find one, the slope in the direction, I should say the slope of f of x, y in the direction What do I got here? V equal to I plus 3j. All right, so as much as we spent time talking about the meaning of these things, the calculation becomes very rote, right? The slope of f of x in the direction of this thing is just the directional derivative in that direction, which I'm never good at writing. Yeah, it's dv f, or I guess you could call it duf, right? If you unitize it, let's just stick with u. So it's duf, which is just the gradient of f dotted with the vector u. U is just our vector direction normalized. So u is going to equal v divided by the magnitude of v, which is going to be, let's see, the magnitude of this is 1 over the square root of 10. Sorry, the magnitude is the square root of 10. So dividing by that, you're going to get 1 over the square root of 10 times I plus 3j. So then the directional derivative of this function f in the direction of u is going to be the gradient of f evaluated at this point. So let's go ahead and find that. The gradient of f is just the partial with respect to x. So y in the I direction plus the partial with respect to y, so x plus 2y in the j direction. And then our gradient at the point we're interested in, which is 3, 2, I'm just plugging in 2 for y and 3 for x. It's going to be 2i. Let's see, that's a 3 plus 2 times 2 plus 7j. Okay, so this directional derivative is going to be that gradient, 2i plus 7j, dotted with this directional derivative, 1 over root 10 times I plus 3j. I would bring the 1 over root 10 out in front, and then just say I've got 2 times 1 plus 7 times 3. So my answer is going to be 23 over root 10. So that is the slope of the surface in the direction of 2, 7, or 2i plus 7j. All right, let's answer a couple more questions. Same surface, same point. So for the same function, f of xy equal to xy plus y squared at the point 3, 2. We could totally graph this. I mean, kind of. Anyway, that's not really the point. At this point, what is the maximum slope? Okay, well, the reason I bring this up is I know we just talked about it, like literally just last example. What I want to point out is I don't want you to do too much work when you have to calculate this. Or someone says, what's the maximum slope of a surface or a function of multiple variables at a particular point? You should be like, oh, gradient, magnitude of the gradient. Right? You don't have to go through this whole process of like finding the direction that's the most and then finding the direction derivative in that direction and then finding the magnitude. No, you just be like, I know that the maximum slope of a function at a point is just the magnitude of the gradient at that point. So the gradient at that point, we already found it. The gradient at that point was 2i plus 7j. So the magnitude of the gradient at that point, I don't really want to write the point there, is just the square root of 2 squared plus 7 squared, which is square root of 53. That is the magnitude of the gradient. That is the steepest slope you get. What is the minimum slope? Negative that. The minimum slope of a surface is always just the negative of your maximum slope, assuming that it's not undefined. So right, the minimum slope would just be negative square root of 53. And it would be in the opposite direction of whatever this was. So whatever direction this is in, which is literally just the direction here would be this vector divided by its own magnitude. The direction of this vector that has the minimum slope, sorry, the direction of the surface that would have the least slope, the minimum slope would be just the negative of that. Okay. Third question. Is there a direction where the slope is equal to 5? Yeah, there is. How do we know? Well, because the maximum slope is the square root of 53, which is definitely bigger than 5. How would we find it? Oh, that's a better question. I just asked it. I just made up a question and didn't think about what the answer was. But let's think about it. So if we want the slope to be 5, okay, how do we find the slope? Okay, well, we calculate the directional derivative. So we do duf del f dotted with u. I might have lucked out and picked something that's easy. I might have. So we want that to equal 5 because we're crazy. We just made something up. So that's not too bad. So del f we know is just 2i plus 7j. We want to dot this with our made up u. Yeah, this is kind of a terrible problem. This is not a good problem. But let me just show you how you would go about trying to solve it. We want u to be the vector ai plus bj. But we also need it to divide by its own length. So it's a unit vector. So divided by the square root of a squared plus b squared. We want that to equal 5. Yeah, this question is probably doesn't have quite enough information to really actually be doable. The other question we could ask is there a place where the slope is 8? And the answer is no, because the maximum slope is not 8. It's the square root of 53, which is less than 8. All right. Was there anything else I want to ask about this? No, not really. Let's see what we got here. Let me go ahead and go back to that question. Let's see, where'd you go here? So let's talk about tangent lines to level curves. It sure is related. Yeah, in fact, that's what we're talking about. We are finding the slopes of tangent lines to level curves in a specific direction. Well, I feel like that might not be what they mean. Yeah, I feel like they mean in the plane of the level curve. Let me take a look at let me see what they're saying here. Tangent line to a level curve. Okay. Yeah. Okay, that's fine. Okay. So let me just go back to the example I have before I get to this question 27 from section 14.5. So yeah. So if we're back, on Mount derivative, and we're on this level curve here at the point 1, 2, 4. If I said what's the equation of the line tangent to the level curve, I specifically mean the line that's tangent to the level curve in the same plane as the level curve, meaning in the plane z equal to 4. So really I'm just saying, okay, here's my level curve. I'm at the point 1, 2, 4. And what's the equation of the tangent line? Okay, well, let's see. I can find the equation of the tangent line. I know that point there is 1, 2. I guess I probably want the z coordinate as well. Maybe not. I don't know. Let me double check. See what they're doing. Yeah, I guess we could do it that way. Sure, that seems fine. So, all right, I'm just going to deal with this in the XY plane for a second. So I need to find the slope of that line, and I need to find the point. How are they writing this? They're doing okay. Sure. So I feel like they're making it in some ways easier, in some ways more complicated than what we really need. Here's the way they're going with it. they're saying that to find the tangent line to a level curve, we're going to take, for again, our function is 9 minus x squared minus y squared. We're going to take the partial. So here is the equation. The equation is the partial of x evaluated at the point times x minus x naught plus the partial of y evaluated at the point times y minus the point, or y minus the y coordinate. And that's going to equal 0. Well, let's see how that works out here. So here, again, the partial in the x direction is negative 2x, and then evaluated at 1, 2, so we're going to get negative 2 times x minus 1, plus the partial with respect to y is negative 2y, evaluated at 1, 2 is going to be negative 4 times y minus 2 equals 0. So that kind of looks like a weird way to write this equation. If we simplify things a bit, what do we get? We get, I'm going to write it as negative 2x plus 2 minus 4y plus 8 equal to 0. And if I was writing this in the normal way, I'd probably isolate y and say negative 2x plus 10 equals 4y, or y equals negative 2/4 x plus 10/4, or y equals negative 1/2 x plus 5/2. Although I imagine their intention is for you to leave it like this. So why does that work? And why does that work? It's a good question. I see. Oh, of course. Yeah. Because you're dotting. Yeah. Right. So basically you're saying, so this is the equation of your line. Yeah, here's why this works. So I want to be able to describe any point on my line, x, y. So what I'm going to do, I'm going to take this vector, that's the vector x minus 1 comma y minus 2, and dot it with this vector, which I know I haven't drawn this very well, but they're supposed to be perpendicular to each other, right? The tangent to the level curve is perpendicular to the gradient vector. So dotting this with the gradient, and the gradient is in the direction of fx, fy, right? That's literally the gradient. It's fx comma fy as a vector, right? If you dot these together, well, if you dot perpendicular vectors together, you get 0. That's exactly this equation here. It is the gradient dotted with x minus x naught comma y minus y naught, and set equal to 0 because perpendicular vectors have a dot product that is 0. So that's why this formula works. Okay, that's kind of neat. So let's go back and look at the question that was actually asked, which is number 27 from section 4.5. In exercises 25 through 28, okay, they want us to sketch the curve f of xy equal to c, where c can be any constant. And then together with the gradient and the tangent line at the given point. Then write the equation for the tangent. Okay. So we are given xy equal to negative 4. Okay, I'm not great at sketching that, but if I solve for y, I know how to graph y equals negative 4 over x. I might plot a few points. I know it's going to be a hyperbola with, like a vertical asymptote at 0, horizontal asymptote at 0. If I plug in x equal to 1, I get y equal to negative 4. If I plug in x equal to 2, I get y equal to negative 2. If I plug in x equal to 4, I get y equal to 1. So it's looking kind of like this. And here's the other side of it. And then we're being asked to find stuff happening at the point square root of 2, square root of 2, square root of 2, square root of 2. No, I'm looking at the wrong one. Sorry, bonkers. At the point 2, negative 2. So we're being asked what's happening right over here. Okay, so we want to find the equation of the tangent line to this point. This one I think is going to be relatively easy. So let me actually just show you guys first what I know what the answer is going to be. So my tangent line is going to do something like this. I don't know if it's actually going to the point 0, negative 4, but here's what I am pretty sure of. I'm pretty sure, well, in fact, so I'm going to do it the old school way first just to show you that it's what we think it is, and then we'll do it kind of the new school way. So what's the derivative here? Well, y prime is, this is negative 4x to the negative first, so it's going to be positive 4 over x squared. If I plug in x equal to 2, I'm going to get 1. I'm not surprised the slope of that's 1. It looked like it was going to be 1. So I know the equation of my tangent line is going to be y minus minus 2 equal to 1 times x minus 2, which is just y plus 2 equal to x minus 2, which is y equal to x minus 4. Great. Well, let's do it the other way. Let's do it the partial, let's see, let me erase this here. So, right, so the way they actually want us to find the equation of this tangent line is by doing the gradient, right? So this is your function, f of x comma y. They want you to do the gradient dotted with x minus x naught, y minus y naught. Okay, so let's find the gradient. So the gradient is just the partial with respect to x, which is going to be the derivative with respect to x, which is y, comma, and then the partial with respect to y, which is x, dotted with, it's the gradient evaluated at the point. So I feel like my notation here is not very good. It's really the y naught and the x naught because we're plugging in the values. But it's this dotted with this. Okay, so the gradient of our function at this point is going to be the y value negative 2, the x value 2. Dotted with x minus the x coordinate times y minus the y coordinate. Now look, right, we're exactly dotting the, my pictures are not great today. The normal vector, sure, that's a right angle, right? The normal vector dotted with the line should give you something equal to 0. So it's this equal to 0, equal to 0, equal to 0. And then when we dot these together, you exactly get negative 2 times x minus 2 plus 2 times y plus 2 equal to 0. If you solve this, you're exactly going to get the same equation. You can divide both sides by 2 if you want, and say that negative x plus 2, right? So divide by 2, distribute the negative sign, plus y plus 2 equals 0. Oh, look, that's exactly y equal to x minus 4. So it feels a little contrived, but so is a lot of this stuff, so that's all right. It's kind of an interesting problem. So if you're finding tangent lines to level curves, you are always just finding the equation of a line with just x's and y's, and there shouldn't be a third coordinate in there. And it's always just the gradient evaluated at the point. So I should really write this as, right, it's the gradient of f evaluated at 2, negative 2, dotted with the vector x minus 2, y minus minus 2. In this particular example. That's what's happening here. Okay, let's see, what else? What else can we talk about? Sure, let's do one that's 3-dimensional, meaning let's look at a function of x, y, and z. So the thing about the examples I've been doing so far is that we've been kind of thinking about whatever you've got as a surface, right? If you look at, in fact, right? So let me expand on this example for just a minute. So if you were going to graph z equal to xy, I mean, it's not easy to graph if you don't already know what it looks like. So if you want to graph z equal to xy, it's kind of not super fun. I'm probably going to totally obliterate it here, meaning not do it well, but that's okay. So here's the thing, z equal to xy is a saddle, but it's a saddle that's not like in one of the usual directions. We have, so in the xy plane, you get either all of the x-axis or all of the y-axis, right? If you set z equal to 0, you either can have x equal to 0, which is all of this, or y equal to 0, which is all of this. And then, oh God, yeah, like, it's kind of like, I might be able to draw it, not terribly. Let's see what happens here. So if z is positive, like if z is 4, you can x and y are both positive, right? X and y can be both like 2 or 1 and 4 or whatever, or they can both be negative. So if z is positive, your x, y values are in the first quadrant or the third quadrant. So we have, sorry, the third quadrant. So we have something kind of, oh geez. Okay, yeah, this is going well. Sorry, you have kind of like a parabola going like that. And then if z is negative, your xy values are in the fourth quadrant or the second quadrant. So they're kind of like that. And then, God help us. Okay, this is going. I've drawn worse things. You guys are like, what is he drawing? Craziness is what I'm drawing. We kind of, so yeah, it's not my best. You can kind of maybe pretend like there's a saddle there. It is a saddle. And so the idea is that for the things we've been talking about so far, we've been saying, okay, like you've got a point on your surface and you're going in that direction. What's the slope of the tangent line in that direction? But the gradient doesn't have to be for a surface. You could totally have a function of 3 variables. And say something like, okay, I've got that, what have we got here? F of x, y, z is equal to x over y plus z at the point 4, 1, 1. And I want to know what's the slope in the direction of, what do we got here? 2i minus j plus 2k. And even though, right, so we can't really, I can't graph this thing. So the way I kind of imagine this when you have a function of 3 variables equal to something is that basically any point in space is modeled by, or you get whatever this value is, right? So you've got like all of 3D space, and then each point in 3D space, you get different numbers. And those numbers might represent like the density at that point in space, right? If you're trying to make some sort of physical interpretation of what's going on. So I want to know, how is the density changing at the point 4, 1, 1 in this direction? Is it increasing? Is it decreasing? Well, let's see. Here's my best guess before we do anything. If this is representing the density, because I've already decided it's density now. If x is getting bigger, then the whole thing's getting bigger. If y is getting smaller, the denominator is getting smaller, so it's also getting bigger. And, well, I should say since it's positive, and if z is positive and getting larger, the denominator is getting larger. So the numerator is getting larger, and the denominator, it's kind of unsure. So this thing could be getting bigger or could be getting smaller. It's really not clear based on our very inept analysis right now. But we can actually find out. So to find this quantity, right, to find the slope, we're going to find our good old, we're going to find the directional derivative, and then we're going to find its magnitude, right? Because the directional derivative, no, sorry. The directional derivative is the quantity. I apologize. So we need to normalize this. So u is just going to be this vector divided by its magnitude. Its magnitude happens to be a nice number. It's 3, right? It's the square root of 4 plus 1 plus 4. So my unit vector is 2/3 I minus 1/3 j plus 2/3 k. And my gradient, okay, gradient, gotta take some partials here. So the derivative of the partial with respect to x is nice. It's 1 over y plus z in the I direction. Let's write this as x times y plus z to the negative first. So when I take the partial with respect to y, I get x times -1 times y plus z to the negative second times the derivative of the insides, which is 1 plus 0. Right? The derivative of y is 1, because we're differentiating with respect to y. The derivative of z is 0. Okay? And then in the z direction, the derivative is z, sorry, it's still x. What am I talking about? It's x times the derivative of this, which is negative y plus z to the negative second times the derivative of the insides, which is 0 plus 1. Okay. All right, so the gradient evaluated at this point, so del f evaluated at the point 411 is going to be, so I plug in 411, I'm going to get 1 over 1 plus 1, so I'm going to get 1/2 I. I'm going to get 4 times -1 times 1 plus 1 to the negative second. That's going to be -1, right? 4 times -1 times 1 plus 1, so 2 to the negative second. That's 1/4 times -4 is -1. So -1 times j. It's going to be the same thing here. -1 times k. That's not too terrible. So then my directional derivative in this direction at that point is going to be the dot product of this and this. Which is going to be 1/2 I minus j minus k dotted with 2/3 I minus 1/3 j plus 2/3 k. Which is going to end up giving me, let's see, 1/2 times 2/3 is 1/3. -1 times -1/3 is positive 1/3, and this is going to be very interesting. -1 times 2/3 is positive negative 2/3. So somebody designed this, surely. We found, so at that point, our directional derivative is 0, meaning we have no change. Meaning if you move at this point in this direction, the value of the function actually isn't going to change. It's going to stay the same.